So we'll start now. Welcome everyone to this month's Mara seminar. Today, Akram from AI for Good is going to present his research on wildlife conflict resolution, Boma and cattle detection in the Maasai Mara using AI. Akram, actually Dr. Akram is a senior applied research scientist at Microsoft's AI for Good Lab, where he's specializing in geospatial machine learning. He has partnered with NGOs to apply AI in resolving pressing environmental issues such as wildlife conflicts, extreme weather quantification, impacts mapping, and climate change. So before he joined Microsoft, he completed his postdoctoral research at IBM Research, where he focused on geospatial machine learning and applied research. Akram has a strong interest in geospatial machine learning, deep neural networks, foundation models, and self or weekly supervised learning. And so Akram is okay. If in case you have any questions and you want to interrupt him to ask them while he's presenting, he's okay with that. So feel free to do that or just paste them on the chat. I'll help him monitor that and he'll answer them all. Over to you, Akram.
Thanks, Millicent, and thank you everyone for your time. I think, Millicent, you already introduced me, so I'm going to briefly mention that I am from the AI for Good team in Africa. This project specifically has internal and external collaborators. So internally, I've been working on this with Caleb Robinson from the Redmond AI for Good lab, and Girma, who's a principal research scientist in AI for Good Africa in Kenya. Externally, we have two partners. So I'm going to introduce them in the next slides, but they are Kenya Wildlife Trust and the Smithsonian Institute. This project, although the title is a bit fancy, really tries to tackle the first step in solving the problem of wildlife conflict between the Maasai people and wildlife animals. It starts solving this by actually trying to map or automate the task of mapping bomas at large spatial regions. So a boma, just to define, is what you see on the right side of the slide. So that's a circular pattern. Sometimes it has other patterns, of course. Shows a boma, which is simply like a counter of where you put cattle to protect against many factors externally, but in most cases, for the cattle not to get lost or to be attacked or stolen. So what we want to do here really is to start by trying to get a sense of the spatial distribution and location of these bomas. That would actually unlock other things, such as creating risk maps and identifying the hotspots of where conflict may arise in the future. So one thing we lead by in the lab is that for every project we take on, we have to connect with domain experts that know the problem more than we do. Again, like my specialty is really in machine learning and data science, specifically geospatial, but I know little about wildlife and conflicts in the region. So that is why we have partners with first the Kenya Wildlife Trust, They have been doing pioneering groundwork in helping the Maasai people, for example, enforcing their bomas, doing spatial planning, economic support through market formation. And their end goal really is to protect certain species, such as lions, cheetahs, and wild dogs. So this is the first organization where we have partners with. The second one is the Smithsonian Conservation Biology Institute. And their expertise really lies in spatial ecology, again, with an interest in endangered species. And they were the ones who actually shared or provided the very high resolution satellite imagery that we have used for this project. So that imagery is normally is for commercial purposes, meaning you have to pay to get that imagery. But through our partnership, we were able to use that data in the scope of the project. So these are our two partners. So a brief introduction on the problem. This is a very important problem in the Maasai Mara ecosystem. So as we know, the Maasai Mara people coexist with an array of predatory species, and as their population expands and they migrate, they clash with predators, right? More and more frequently. The conflict looks like the figure you see at the center of the slide, where predators hunting in the wild, if they get to encounter a weakened boma, they can attack the cattle and kill the cattle, and that affects the settlers enormously, which leads them to kind of kill or poison the predators in indiscriminatory fashion. Again, this problem has been more and more prominent because of the expanded population. And our contribution here, as I mentioned in the beginning, is that we want to start by getting a sense of where the hotspot regions are by mapping the bomas first, and specifically the active bomas, the bomas that have that are still being used by the settlers. So we want to use AI and apply it on satellite imagery to automatically identify these hotspots of conflict. So that's the task. Why AI and not really just doing it yourself, right? That's an obvious question. Again, the main factor here to consider is that the region of interest here, which is the Maasai Mara region, is huge. If you want to download a bunch of very high resolution satellite imagery and do the annotation yourself, you'd need to spend a long time. Many days and days of annotation. And even with that, through to human factors, you may get erroneous labels in many subregions where you may make mistakes. So the thing with AI is that it's cost effective, right? So once we train an AI model, we can scale it automatically to all of the region of interest. It reduces the time and manpower costs. So it only deals with compute after the learning process, of course. It is scalable, right? So once we train on one region, we might be able to scale it to adjacent regions in space and time. And it is also consistent in terms of performance. So we can be sure that like the at least in the region of interest that the model was initially trained on, the performance would hold and the model would produce quality predictions. Okay, so the thing we start with here really is some satellite imagery, right? We don't have labels for this. Or to be 100% accurate, the labels that we have are not indicative, or they don't correspond to the imagery at that point in time. So we don't have really historical labels of bomas at that specific time or adjacent times to it. And we start with some very high resolution satellite imagery, and we want to learn how to identify these settlements. the Boma settlements. So we can break down the problem into two tasks. So the first one, we just simply want to find the bomas, right? These circular shapes that I've shown in the first slide. And for that, we want to train the most direct ways to just train like a semantic segmentation model to identify the bomas. Now, when I say settlement, that means that the Boma may probably be active, and that is why we aren't just interested in the Bomas, but also in the surrounding buildings that typically exist with these Bomas. This is where people live beside their cattle. So we are interested in two objects. The first one is the Boma itself, and the second one is these small buildings. And we want to train a segmentation model to detect those entities. The second one is that we want to kind of detect if the Boma is active in a very direct way. And in this case, we just want to detect if there is cattle inside the Boma, right? At the time where the image was captured, which is early in the morning. So two tasks. The first one is segmentation. The second one is really can be considered as like a classification task. Given a Boma as input, a Boma patch or a Boma image as an input, classify if there is cattle inside or not. So the final pipeline is just the concatenation of these two steps. First, you want to do segmentation. You want to identify where the bomas are and where are the adjacent buildings. And then second, you want to extract the patches that correspond to bomas and run them through a second model to tell you if they are if the Boma is populated, if each Boma is populated or empty. So starting with one image, or let's say we start with some satellite imagery, and because we have no labels, we want to do some labeling. However, we don't know how much labeling do we need to solve the problem. And that is why you see on the figure on the right, we adopted a kind of an iterative approach to labeling. So we start with satellite imagery, right? And the bomas are visible in the satellite imagery. However, that satellite image is huge, so we cannot inspect all of the regions in it. So what we do is that we zoom in into one region and we add a few labels ourselves. So we create a few labels. And then after that round of labeling, we train a model and see what kind of performance that model gives us. And in terms of scalability, can it point us to other labels that we can add automatically? And that is where the iterative aspect of this comes. It's in getting feedback from the model and using it to add labels, add the labels that are most valuable to the next iteration. And once we iterate over this cycle for a few times, we'll be able to converge to like a satisfactory performance and take that model and like kind of run it through the whole region and export a data set. So because we don't know how many labels do we want upfront, and because we don't have a sense of the variability of the patterns in the image, we relied on an iterative approach and we relied on model feedback to know where to label and to provide the most valuable labels to the model for the next iteration. So that is the approach we adopted here. The first step, though, is that we need to acquire the data, right, and process it for machine learning. And this we use for this we use the Maxar catalog to just identify the scenes or the images that we want to download. We get them in a raw format, and we have to do some processing, of course, for deep learning. First, we want to do georeferencing and alignment, and for that we can just use the JDAO tools or utils to automate this task. And then after that, what we have really in this case, in this project, is that we had two scenes, two satellite images that overlap. And because they overlap, we want to create a mosaic first. A mosaic is just when you merge two images into one. via some mechanism, such as like give me if two images overlap, just give me the most recent pixel, or average, or some kind of other mechanism to do that kind of merging of the images. So we created mosaics that are based off of two images. So that's the first thing, just to get a single image. And then I forgot to mention that we had two files. So the first file has 4 bands, RGB and near, right? So it's 4-band satellite imagery. And then the separate file is the panchromatic band, which is actually the one that has the highest resolution, that comes in 50 centimeter per pixel. And the reason that we have 2 images here is that RGB and near have a very low resolution. And the panchromatic band, or the pan file, has a very high resolution that is typically used to upsample the RGB. So we created separate mosaics for the 2 files. However, by the way, the 2 files cover the same region and have the same timestamp, so they're not in any way different from each other. And then for the purposes of like deep learning, we standardized both images separately again. So standardization using bandwise mean and standard deviation. So we standardized both images. We upsampled the RGB near just to match the panchromatic band in resolution. And then we just stack all of them together to save the final image. Now, the final image is just a single image that has 5 bands, RGB, near, and pan. We know that the panchromatic band has the highest resolution, while RGB and near are important because they cover different patterns that we want to detect, right? So the final image is what you see on the right. To summarize, really, we start with 2 images, and we have to do some processing to make it consistent, to make it to standardize it for deep learning, to create the mosaic, and have a single image that we can use for labeling and we can use for learning too. So as I mentioned, we exported this input image, right? And the input image covers the blue rectangle you see on the map, right? So it covers that whole region. That is approximately 3,600 square kilometers. Again, coming from 2 scenes, and as you see on the far left side, two images. They have the same date. And once we have this image, what we can do really is to add a few labels. So take the image to GIS software and do some labeling ourselves. First, we need to determine the training and validation region, most importantly. And in this case, we have a spatial split. So it's not a random split. So there is one region you use for training and a separate region that you want to validate your model on. But we have to validate, we have to annotate these regions too, right? So we have 3 splits there, train 1 and 2 and 3. The 2 and 3 are at the bottom of the image. And then we just create a few polygons, right? That show where the bomas and buildings are. And the zoomed out image that you see on the far right shows these polygons. In green, these are the bomas, and then red represents a building. So once we have this, right, like once we have the image, we take the image, we add a few labels. We can use these labels that we created ourselves to create a mask, a segmentation mask that matches the original image. And once we have the image and a mask, we can just train a segmentation model on it. So that is what you see here, right? On the right, I have the first train val split. In green, the bomas. In red, the buildings. The buildings and bomas are everywhere. They're in the training and validation. These are handmade, right? Like manually created using QGIS. And we use them to export a mask. And once we have that mask that has the labels for every pixel, we can train a model. Now, that's the first task, which is segmentation. The second task, which is classification, requires patches, right? It requires these patches of bomas and a label that can either be 1, which means the boma has cattle inside, or 0, which means the boma is empty. So, but there's the second labeling task is much easier because we already done the work to label many bomas. So we can export the patches automatically from the images and do hand labeling very quickly on these patches, and classify them as either populated or empty. And that's for the second model to be trained. So the number of geometries you see there, the breakdown, that at the end, after we did 4 iterations, we ended up with 4,000 labels. 800 of them are for bomas, and the rest is for structures or buildings. This is after we've iterated multiple times. However, when we started very low on the number of annotations. For the learning methods, we did a few things. So first, because we don't have a lot of labels, we used ImageNet pre-trained encoders, right, for the segmentation model. We used class weighting because the classes are very imbalanced. So the number of bomas in the very large region are very few. So we need to have class weighting on the last function to help learning. We tried quanti-normalization. It's a technique that is similar to standard normalization, but instead it's similar to min-max normalization, but instead of taking the min-max, you take the quantiles, like the first and 99th quantile to do your normalization. We tried many techniques for augmentation and other things. Now, this really falls into the realm of hyperparameter search, where you're not sure which things will work or not. And what you want to create is just like a search space where there are many options, and your data module and task class can support these options, and you can do hyperparameter search. Now, we don't really have to write code for a lot of this because there's already support. So first library I want to highlight for geospatial deep learning is TorchGeo. It's actually by the AI for Good team. And it really helps. It helps you train deep learning models on geospatial data without worrying much about, for example, patchifying your image into small patches and like manually loading them, or doing, for example, CRS conversion where you have like different images that are not perfectly aligned. All of that really is handled by TorchGeo. The way you do, especially how you do sampling, like the data point sampling for batches. So we have used TorchGeo for this. We've also used for segmentation, we use the library called segmentation models for PyTorch. And it really has support for many types of segmentation architectures and backbones. And that is just to automate the process of hyperparameter search, try many things and see what works best here. Again, all of this really is tailored to the first task, which is semantic segmentation, not the second. So the results that we got after doing all of that are expressed here as F1 scores, aggregated on all pixels. And as I mentioned, we had to do 4 rounds of labeling, training, prediction, and examination, and add in more labels to reach this performance. So the breakdown here is for F1 scores for Boma classification, which is 0.85, structures separately 0.79, and then for classification, which I haven't talked about much, because I think the task itself is kind of simple. So as input, you have the patch, and you have some kind of encoder that would take the patch and give you a representation, and then you'd classify it based on that, right? It's a relatively simple task because you just want to figure out if there is something inside the Boma or not. And for that, we get an F1 score of 0.97. The challenge here in doing this wasn't really about like the deep learning architectures and any of the ML algorithm sides, but more about the labels. So you start with this huge image. You cannot really look everywhere. You can only zoom into one place and maybe inspect it. And you want to add labels in an efficient way, and you know the labels are scattered, right? So you cannot really create a few labels and say everything else is negative, because you're not sure if there is or there's or you're not sure of the existence or absence of other bomas in other regions. So you cannot automatically assume that like because I've labeled this, I'm gonna assume everything else is doesn't contain bomas. Um, and you cannot spend too much time doing the labeling because some bomas are similar to each other, so that won't contribute as much to learning. So what you end up with really is actually a scarce data setup. Even though we have a huge image here, we cannot feed all these pixels as training information just because we don't have labels for them. We leave majority of the pixels as ignored, like we don't even label them and the model ignores them during training. This introduces challenges, like when you're operating in low resource or low label regimes. Even though you have a huge image, you cannot really hard label all of the pixels yourself. So you have to select even the negatives, even the regions where there are no bomas. You need to know where to select those to provide most information to the learning process. And this is what we did here through our iterative procedure to add more and more labels. The labels were really not two, not just buildings and bomas, but three. So you have buildings and bomas, but you also have the regions that are not buildings and not bomas, and they are worthy to be added to the training. And the remainder of the pixels are just being ignored. So they have the flag or the label value of 0, which means, and we instruct the model to actually ignore these pixels that are labeled 0. And 1 is Boma, 2 is building, and 3 is negative. So it's a different setup from classical like segmentation on natural imagery, where you'd expect the whole image to be segmented already. In most data sets, all of the images are segmented perfectly, and you just want to run a model. In this case, you cannot do this because you're not sure where there are bomas, and you cannot have assumptions on the rest of the pixels not having anything interesting in them. So that's the main challenge, which really leads or led us initially when we were iterating early on into solving a related problem, which is this artifact thing. So let's say we label a few bomas, we train a model, and then we take that model and we run it through a validation region to see what it predicted. What it typically outputted are these weird artifacts, as you can see on the right, where it's actually capturing the boma. So you can see some perfect squares there and so on. So it really captured the bomas, but it also starts like to produce these artifacts because it's unsure of these pixels, the patterns that it's detecting. This really comes from the fact that the original training, the input image, wasn't fully annotated. So you get very high recall, but low precision, right? So the model is capturing all of the bomas, but at the same time, it's producing a lot of artifacts, a lot of false positives. So we struggled with this initially when we were adding labels. A simple solution to this, which is not so simple if you have a huge image, is to just label everything. So if you want to eliminate artifacts like this or false positives, you just need to show the model the negatives as much as possible, meaning you need to add a lot of like non-Boma, non-building type pixels and all of them for it to be regularized and be able to scale with no artifacts. However, this wasn't our case. So what we based our solution off is an observation. So what we notice is that when the model is being correct, meaning it predicts, it detects the bomas, it's typically very certain about the fact that there is a boma there. So the probabilities are high. The probability that is outputting is high. However, when it comes to these artifacts, there's high uncertainty. So the probabilities are kind of balanced, and it's barely making the threshold. The false positives are kind of barely making the threshold to become predictions. And so that led us to think about ways to mitigate this without adding labels. Again, the solutions that I mentioned, the first one is I already mentioned. That one, you just like label as much as possible, and you try to capture all of the objects in the image, and then you assume that the rest are negative, or you make sure that the remaining pixels have the negative label, meaning they're not the object you're interested in. That leaves no space for the ignored pixel, right? So everything is labeled in that case. The second solution is to try to, like, similar to what I was saying here, like observe properties that has to do with these artifacts and introduce some kind of regularization mechanism against it. So in our case, what we would do is that we have like a few bomas labeled, a few buildings. We know that there are bomas in other places. We add negatives too, but we also penalize the model for being uncertain. So we encourage the model to only predict Boma if it's really sure that it's Boma, and do not predict otherwise. So we do this by kind of changing the loss function. And in this case, it's a simplified version of cross entropy. So you have the definition of cross entropy, right? That has to do with the labels and the predicted probabilities for every pixel. And then entropy itself, right? The definition of entropy doesn't really require labels. Entropy only has to do with the probability. So that's H, right? H is similar formulation to cross entropy, except that it only operates with probability. So probability log probability. So what we do really is that we weight these two terms together. So the loss that we introduced is a weighted loss, where for the pixels that are labeled, we're using cross entropy. And for the pixels that are ignored, meaning the pixels that are not labeled, we just use entropy. We tell the model, look, for the pixels that we don't give you prediction, we don't give you labels, just be as certain as possible when predicting. And we kind of like test this, right? So you can vary the amount of negatives, you can vary the amount of positives, which are the bomas, across the training regions that we have, as you can see on the right, and see how performance is. And what we noticed is that in low label regimes, so when we're dealing with like less than 20% included negatives, meaning there are a lot of pixels that are just ignored, if we add that term, if we add the regularization term, the model has much better performance. So it's producing less and less artifacts, right? This is very helpful where you don't want to spend time like annotating 1,000 or 2,000 labels. You only want to do a few, like maybe 50 labels, and you want to regularize and get decent performance on that task. So that's what we got after we did that. Here's an example, a very simple example. So here we are training on like 10% negatives. 10% of the region is annotated negative, which are the polygons, the shapes there you see in gray, in the gray color. And then we have the bomas, right? They're annotated correctly. And you see that difference, right? So in the bottom left figure, F1 score, we run the experiments 10 times for the two setups. The first one uses cross entropy, the second one uses cross entropy and the regularization, and we can see that the performance is much better actually in these low label or low negative label regimes, which is very good, because in many cases you don't know what's outside. You don't want to annotate everything else as negative. You want to actually only annotate a few regions as negative as you see fit, and then train a model and expect good performance. And the effect of the false positives that come from this unregularized model disappear when we add regularization. The model is more conservative. Oh, these are predictions over the validation region. So using only cross entropy results in these like big number of pixels that are just false, like false positives, that make it across runs. So these are for 2 different runs for each setup. And then when we add entropy regularization, the term that I was presenting, the model is like being more conservative, right? So all of the false positives, or at least the obvious large regions of false positives disappear. And then we have a much more conservative, much more correct prediction coming out of the model. This, by the way, really, the regularization part of the loss function is not really dependent on the original loss function itself, as you may have observed. Like cross entropy is a loss function itself. It can be weighted with the regularization term. That loss function can be replaced with any other kind of loss function. So you can put the F1 smooth loss function and still weight it against the entropy regularization. So entropy regularization is not really dependent on the loss function because it operates on a different domain. It's operating on a domain of unlabeled, the unlabeled domain where we don't have labels, and it's weighted according to that. So they're not really it's not really ingrained in the loss function definition. It's just an added term to the default loss function that you have we have already been using in this case. So what I mean is that the term is agnostic to the loss function that we are using. So what is the result of this really is a data set. So what we wanted to share with our partners is just a spatial distribution of where the bomas, where the buildings exist in the huge ROI that we are interested in. So after we trained the model and regularized it, and it was ready for the first round of testing, we took that model, we run it through the whole region of interest, the whole image that we started with, and then we got predictions, right, for the bomas and buildings and also the populated bomas. And the data set comprises around 4,000 empty bomas, 160 populated ones, and more than 20,000 structures. We really, after doing that kind of prediction, we had to do some post-processing. We wanted to move from the raster space where we only have like pixel predictions to actual geometries. So that involves like rasterizing not rasterizing, but vectorizing the raster predictions or the image predictions. We wanted to turn them into geometries and then simplify the geometries, remove outliers. For example, we noticed that there are many predicted buildings that are very small to actually be buildings. So we did some kind of manual outlier removal. We also smoothed out the geometries. We did some filtering based on compactness and rectangularity of these shapes, especially of the bomas, because we noticed that bomas can either have a circular or rectangular shape. So because you have a template of what you'd expect your object to look like, you can take that template and match it against the prediction and see how alike it is, and maybe do some filtering based on that. All of this to actually end up with a quality data set that captures the object, it captures the geometry of the boma or the building, and be useful for our partners. So here are a few examples. On the left, you see the input, right? The input imagery. And on the right, you see the input plus like overlaid on top of it, the predictions. In green, we have the boma. In red, we have these buildings. They are quite small, by the way. And the rest is just ignored, right? So these are the final geometries that we post-processed. So this is the first example. Here's a second example. This is interesting because the model is capturing the bomas, but you can see some boundaries there that aren't captured. And we might argue that it is because of the color. So the bomas are not just about the boundaries or the fencing, but they also have to do with the color inside the boma. The color is typically darker. So the model is using that information too to do the segmentation. So if it sees that the color is very light, it would assume that maybe this is an abandoned boma. It's not being used anymore because the ground color isn't as dark as the examples shown in the training data set. And for buildings, it is doing a good job in capturing all of these small buildings that I'm pretty sure I can see them myself here. But if we zoom in, we can see them. And here's the final example, right? The model is being quite good at capturing these rooftops for the buildings or the structures. For the bomas, it may get confused. So it has the preference for the color, but there's also the fence or the boundaries. Sometimes it captures the whole boma. Sometimes it's more conservative and it focuses on the dark color inside the boma. And that is a thing we can improve on. Now, I wanted to end with a few lessons, a few learnings throughout this project that might be interesting to you. First, when we label for geospatial, we tend to create the polygon, and that's it. It represents the boma, and we train. However, the adjacent pixels surrounding it, because we do that, the adjacent pixels are ignored, right? So they're not labeled. We label the bomas, we move around, and we leave everything as ignored. If we train a model using that kind of mask, the model is not going to be penalized if it spills, if it starts predicting outside the boma, immediately outside it, right? So you're going to have these ugly predictions. They still capturing the boma or the entity of interest, but then it's going to spill outside of it and predict all kinds of things as positives, which in actually they're negatives, they're mistakes, but the model doesn't know because you set the pixels, the adjacent pixels, as ignored. So a simple mechanism here that was very helpful to us and doesn't require actual manual labeling is to take all of the polygons and automatically create a buffer around them that is negative. We say to the model, don't spill outside this, because outside this polygon, there are negatives. These are not BOMA pixels. These are non-BOMA pixels. So we kind of force the model to stick to the region or the pixels that really represent what we want to detect, and not be and not spill outside and start predicting many adjacent pixels as positives. Again, here, the lesson is that models are really lazy. So you cannot assume that they're gonna learn what you are seeing as patterns in the image when you're inspecting the image yourself. And we need to find techniques to make it harder and harder for the model to learn or to capture the patterns. That's the only way where the model is going to capture the actual patterns that we wanted to capture, and not some actually easy pattern that it figured out how to map initially. So that's one way. The one easy way to do this is to just add negative buffers around the objects. This is related. By the way, this dataset is not the BOMA dataset. This is a building damage detection dataset. It has to do with label quality. So in the way we iterating and annotating for geospatial, we definitely don't want to be lazy and just ignore whole regions because they look difficult to label, or label a block of many buildings as, for example, healthy buildings, while we're not sure, and kind of take these shortcuts. We kind of resemble models when we do that because models are lazy too. What we want to do instead is really put the effort in the labeling process and try to label patches that are the most difficult to us to label, but we still know the labels. We shouldn't label things that we don't know the labels of course, but we should label difficult regions. So for example, this one is difficult because there are buildings, and there are some buildings we're not sure if they're damaged or not, and the boundaries between buildings is kind of ambiguous. So we want to strike a balance in the sense of first tackling diversity, checking the regions that are most difficult, and labeling them correctly at the same time correctly. So don't label blobs of buildings and so on, but label individual buildings or individual damaged regions. And as you know, as much as possible, have adjacent different classes close to each other when doing the labeling. That would force the model to learn something instead of producing arbitrary maps. Because at the end of the day, the model would produce something similar, at best, something similar to what you give it. So if you give it something that is lazy and just obvious to you, it will probably be bad at the final task. So this second lesson I had to go through because initially I did some lazy labeling and that didn't give me good results. And I had to go back and create more interesting labels and dense labels, diverse labels for the model to be learning effectively. The third lesson has to do with the data scarcity. So data augmentation is a huge deal in satellite imagery, just because you can do so many things to a patch, like a satellite patch. And that really helps in learning because you're enriching the data set and regularizing the model as it's learning. So default options when we do semantic segmentation on satellite imagery is to just add horizontal and vertical flipping to the patches, rotation, cropping, color jitter, and other ones. There are other more advanced augmentation techniques. And this is the third lesson that really would help learning if we are dealing with or using just a few labels, not a lot. So this is the quite important to actually to start with and not to think about later, to just start by default doing data augmentation on the satellite patches and as much as possible. Now moving to the impact of all of this. So as I mentioned, like the model's job is to produce a data set. The data set was taken and processed, vectorized into polygons. And what we did after that is that we just shared the data set with our partners, right? So for example, the Kenya Wildlife Trust can use such data. Once you map like this huge region, the Maasai Mara, to map it of bomas and buildings, they can actually join that data sets with their own data sets, protected areas and so on, and see and try to create a proxy like risk map that would help them prioritize where to put resources. So for example, they help communities in predator Boma proofing, and other things, the educational, anti-poison campaigns, and so on. Such data sets would show them, hopefully, where to go, right? Where to conduct the operations that they want to do and route resources most efficiently. And that's the downstream impact. So we continue to work with our partner, providing the data sets, improving on it to help them, help the communities, and protect animals. So that's the end goal for us. That's what we're working on right now. As next steps, as you saw, the labeling itself happened visually. So we just did visual inspection, and we added the labels using the satellite image. So first thing we want to do is in-ground validation, and the partner can help us with this. This involves actually a team going outside and checking if bomas exist where we tell them they are, and give us some ground truth information that we can use to evaluate the model and not only validate it from a machine learning side, but also evaluate it to be surely useful. We want to scale the model to other regions and times. So we actually have access to other satellite images in other times and other regions adjacent to the region that we started with, and we want to take the model and scale it across space and time and create a spatio-temporal data set as a result. That will be very good for research as it will be for our partners. That would unlock other things, such as like analyzing the change in the distribution of these bomas, like how many of them are created versus abandoned, their areas, how the areas of the bomas change, and as I mentioned, like the growth and churn of the bomas, the tracking community and migration patterns, and also adjacent, like joining that with predator conflicts would be very interesting to explore. So to conclude, we just used AI to do large-scale spatial mapping of bomas and structures in the Maasai Mara. We mapped a considerable amount of bomas and structures and populated bomas. The impact for us is really, in this case, downstream to our partners. So we continue to collaborate with the Kenya Wildlife Trust, the Smithsonian Institute, to improve the quality of the data set and to help derive data sets from it in the future. And finally, of course, we want to contribute to open data initiatives, publish the data sets and the model to accelerate research and collaboration in conservation. Thank you. That's it.
Quite enlightening. Thank you very, very much, Akram, for a very wonderful presentation. We have one question, but we are like 3 minutes to like 4. We have just one question from Edward Omburi. I'm not sure if he's around. I think he has left, but maybe you can just answer this. How do you tell the difference between the sheep, goats, and cows, given that your focus is on the in the cows? Sorry.
We can't really. So one of the things we explored in the beginning is trying to do like unit segmentation or detection, like object detection on the cattle units and their types. It's not possible with the resolution we started with. So 50 centimeter doesn't give you that kind of precision in the image. So what we do really is we consider everything as cattle, cow, sheep, or other types of cattle. They are just cattle, and we just want to detect the presence of cattle, not some specific species.
I mean, that's really great. My question, I mean, I wanted to ask if the predicted Boma regions actually exist, and I've seen that that's part of your like next steps, the validation part, and this is quite great and exciting research. Yeah, so happy that you could share it with us. I don't know if we have other questions from the attendees.
Yes, actually.
Yes, please go ahead.
So you mentioned that you use this iterative approach where the output of the model was used as input for the next iterations, right? So I'm wondering if the model makes a mistake in the first iteration, then it will only become more confident about this mistake in next iterations. So how do you prevent this from happening?
Yeah, so that's a great question. I kind of didn't explain it correctly. There was a human in the loop. So we don't immediately add the labels that are predicted by the model in the next iteration. We manually validate these labels because it's a huge region. We also wanted to quickly know where the settlements are, and the model, the first iteration of the model was really good at showing like approximately the regions to zoom into and add labels, but not to like be 100% confident in it and automatically add the predicted labels into the next iteration. So it was only an assistant to us.
Oh, okay, makes sense. Thanks.
Any other question? Ishmael, I don't know if you have a question or you just unmuted. Okay. Exactly. So thank you very much again, Akram, for a great presentation, and thanks everyone for joining our seminar this month. Thank you.
Thank you.
Bye.